Exactly. All right, well, I'm going to introduce Jack. So it's my pleasure to introduce Jack Holt. He's an old friend. He's been at University of Texas for a number of years before he left and went off to the University of Arizona. So in fact, little specifics to the Center for Planetary Systems Habitability is that Bill and Jack were talking about starting a center long before I got involved. It didn't quite come together, and then Jack went to Arizona and started his own center, the Earth Dynamics Observatory. Yeah, right. And then we ended up starting the center in his absence. And Jack is back to talk to us. So, yeah, subbed here.
It's a good handoff. Yeah.
So yeah, Jack's a professor at the Department of Planetary Science as well as Department of Geological Sciences or Geosciences at Arizona. The Department of Planetary Science is also known to a lot of people as Lunar Planetary Lab, which you'll see up there.
Yeah.
Which was both external and then now is part of the university, right? It's had interesting.
Yeah, I mean, yeah, sort of.
Sort of. Okay, let's see. And he's done an incredible amount of things in the world of planetary science. So he was on the Charade team. He has done radar throughout the Earth system, was a part of everything from Ice Bridge to a number of exciting, planetary or Earth-based applications of planetary radars. And then most recently was awarded a fairly sizable grant to basically study Northern Hemisphere and Southern Hemisphere glaciers. Is that
It's
right?
Northern Hemisphere.
Just
Arctic glaciers. Yeah.
And Arctic glaciers.
Yeah.
Right. Yeah. So using airborne radars and kind of not quite a follow-on to Ice Bridge. It's a really different focus. But
Kind of, yeah. But it leverages Ice Bridge.
Yeah.
Yeah. But yeah.
Let's see, and he will be around the next 2 days. We're trying to talk him into coming back for a longer visit as visiting scientist later in the year, potentially. And there is a little bit of space left in his schedule. I think he's got a virtual at 2 o'clock, which the person who's at the wrong campus said that they're happy to give that up. And he's also going to be up at the Pickle Research Campus tomorrow. So from 1 to 2, he has that slot open as well. We're going to have a happy hour with him at Crown and Anchor that some people are going to join at 5 o'clock for anybody who, or 5:15, I guess, for anybody who'd like to go to that. And I have a little bit of space for the dinner as well, if folks would like to join Bill, Anita, and myself for dinner tonight. I think that's it. But anyway, Jack, thanks very much for coming and giving us a chat, and welcome.
Thanks. Thank you, Sean. Thank you for inviting me. It's really great to be back here. New faces, some new faces. I do love this place, and it's really fun to come back and give you a little update on some things I've been doing on the Mars side. Didn't have time to. I can't really talk about the Earth stuff that much today, but some of it is Earth work relevant to Mars. So that'll be cool. So background on this slide here is a. If I get the to advance. Advancing, of course. How about I just click on it?
Click on it. There you go.
Wow. This is an image. It came out of a paper Collins Davis led 2018 from High Rise, and they also it's which is a camera on Mars Reconnaissance Orbiter showing evidence for a cliff with exposed ice and basically it's high middle latitudes and where ice is unstable at the surface, so this cliff is retreating back, so it's an actively sublimating scarp, and it's backed up by spectrometer data as well. So it's pretty cool. Adds to some other evidence which I'll show for quite a lot of distributed ice in the near surface of Mars. And so why did I make this title? There's been like a lot of emphasis on accessing this ice for various reasons, driving NASA priorities. So it's kind of thought, it might be a good time to kind of sit back and say, okay, what is the situation here? And if you're not familiar with Mars, maybe it'll give you a little good overview, because there's always news stories coming out, like it seems like every week, like more ice found on Mars, or maybe water, maybe not, but so it'll be a bit of a review, and if you're already a Mars scientist, it might be, they're pretty much review, but I'll be talking about some terrestrial analog work that might be of interest and different. None of this work would have been possible without a bunch of students, and some of them used to be here. The top two in particular, Roberto and Tyler, contributed a lot to the terrestrial analog protocol show. But some of the Mars work that I'll also bring up was done by Eric Peterson and Cassie Sturman. They both graduated from UT. Tyler started at UT, moved to Arizona, graduated last May, and is now a postdoc at WashU. Starting at the kind of high level, this book was a surprise to some people, but the top priority Mars mission in the new decadal survey after Mars sample return, which is the elephant in the room, is Mars Life Explorer, or MLE. Now, I don't know if you know much about Mars sample return, but it's a great, exciting project, but also a giant money hog and causing problems across the solar system. So who knows what's going to happen with it? So Mars Life Explorer might happen in 30 years, or it might happen in 10 years if MSR gets canned. Who knows? But this mission is a landed mission based on pretty current technology, well-developed technology mostly, to seek signatures of extant life within the top 2 meters of the surface of Mars. So they plan to drill into ice where they think ice is there based on orbital data. And kind of amazing to me is they think they can just pick a site based on orbital data and just go there and drill 2 meters down and hit ice.
I was about to ask that question.
Yeah, so that's kind of a motivation for this talk, really. It's like a cautionary tale of like how hard it is to do that. And if you're going to spend that much money, why would you gamble like that? Kind of a similar case in ISRU, NASA and SpaceX both talking about sending humans and using water ice as a resource. SpaceX even plans to, if you believe it, send Starship there and then mine the water ice to make rocket fuel to bring it back, like not even take the fuel to come back when they go. They just want to know where to land, but they don't really want to pay for any reconnaissance missions either. So the engineers want a low latitude site, and as I'll show you, that means deeper, ice stable. And so the big question is, how deep is it? How pure is it? How difficult will it be to access? So 2 big motivations right now that are driving some missions. A big picture overview. Mars is a cold desert. It's been that way for about 3 billion years. Ice does move around, as I'll explain. But you've got the the polar caps where water ice is stable at the surface. The south polar cap sits higher topographically than the north, so it's colder and you can actually have CO2 ice at the surface. But the bulk composition of the south polar cap is water ice. As you come down in the north, you get into a lot of shallow near surface ice. And then there's starting to get into paraglacial features like polygons, some craters in both northern and southern hemisphere. And you get viscous flow features, including debris covered glaciers, which we'll talk about more. And even in the equatorial regions, in the very high elevations, there's evidence for tropical mountain glaciers in the past. So that's the current situation, but Mars' orbital parameters change quite a bit over time. This is a plot from Lascard 2002 showing obliquity and eccentricity, which is translating into insolation over the past 10 million years. In Earth's obliquity, it's a little wiggle around 23 or so. Mars is all over the place. And so you can easily have obliquities between 15 and 45 degrees. And what that does is basically it just shifts the stability region around. So currently it's stable at the poles, we're at a low obliquity state, fairly low, pretty similar to Earth's actually. And I forgot to mention the reason this is the case is that Mars doesn't have a big moon like Earth, and it resonates more with other planetary bodies because it's that's what Lascard told me anyway. He has to do the calculations of all the planets at once. going back in time, which is pretty amazing. So basically the ice moves around, there's no ocean like Earth, so you don't build ice sheets, but you can build ice sheets, but they just move around. So at high liquidities, you actually end up getting ice at the high elevations at very low latitudes, equatorial. And then as it comes back, you start moving things to the middle latitudes. So what happens is, in a lot of cases, you end up preserving ice under a blanket of regolith, and it can be preserved for a very long time. Now it probably doesn't always get preserved during these big shifts, but sometimes it does. And there's a lot of evidence for that. So this is a pretty nice compilation, building a model, but it's based on measured surface temperatures and thermal inertia from orbit, with a 2-layer system of regolith overlying ice, so PQ and all. So you can see in the high northern latitudes, according to this model, you should have ice within the top, say, 20 centimeters or so. Or it can exist, and it probably does based on the thermal data. They look at how the subsurface ice can affect the surface temperatures. And then you get into closer to a meter depth at these latitudes, and then basically it's much deeper than they can ascertain with the data below about 40 degrees latitude. So in order to validate that, we've got some observations. So the Phoenix lander was right up here, a little over 60 degrees latitude. The thrusters blasted away some surface, debris and saw ice, like the image ice there, and then they'd could scoop down just enough to get into ice, and then they could watch it sublimate away. So that's pretty valid. We've got a bunch of freshly exposed impact craters. That's what the first paper by Shane Byrne and others. They monitor this with repeat CTX data on Mars Reconnaissance Orbiter, MRO. And they see a splotch, and they go in with high rise and zoom in detail, and then do repeat measurements and watch the ice sublimate away. So that crater is probably a few meters across. And so it's not excavating very deep, but it's getting into the ice. And there's one of the icy scarps, like I showed in the first opening image of opening slide. So those are all in these white diamonds. So there's a number of those around, not a lot. The impact craters, the red ones are where there's fresh impacts, but there's no ice exposed. So the observations are pretty consistent with those results. But one thing, I did notice a couple of quotes from their paper. The observed lateral depth variability at various scales may pose its own set of challenges for ISRU. So they do see a lot of variability. And they can't distinguish between massive ice, which would be, what you really want, and poor ice, because they have similar thermal properties. So that would be a very different scenario for both of those, driving motivations from NASA. All right, so to get deeper into the subsurface, let's talk about radar. That's, what I've focused on the most. And there's a couple of radars orbiting Mars. Mars is on Mars Express, probes very deep. The one relevant for this topic is the shallow radar, or SHARAD, on MRO. It's a 20 megahertz radar sounder, 15 meters wavelength. Its bandwidth yields a vertical resolution of about 10 meters. Horizontal resolution is about 0.3 kilometers along track, 3 to 6 cross track, basically resulting in the Burnell zone. And it's been in orbit since 2006, still operating. We're still targeting things, collecting data. It's kind of amazing. It was provided by the Italian Space Agency, and they also built the radar to Marsus on Mars Express. So if you're not familiar with radar, basically you're going after subsurface structure and composition, and it's sensitive to changes in electromagnetic properties, primarily density and conductivity. So this is a little cross section of part of the North Polar layer deposits from SHARAD, showing layering in the radar data, and you see lots of layering in visible data. Works beautifully there. But we're going to look at some shallower stuff. So this was basically the paper that my student Cassie Sturman wrote. And basically it's from the northern mid-latitudes, Utopia Planitia. And there's a lot of periglacial features there, evidence for at least at a minimum ice in the subsurface in the past. And so people were wondering, is there still ice there? How much? So there's these scallop depressions, and they're basically subsurface features. Polygonal terrain indicating subsurface ice, like you would find, say, in the dry valleys of Antarctica or a lot of places in the Arctic. And lots of layering in these exposed mesas. So the radar data, I will do this on a laptop so people online can see it better. But you got sort of this little bit fuzzy surface return. It's kind of a rough surface. And then below that, you get a reflection. It's a little bit discontinuous, but you can see the base of these, basically the higher unit. The bottom panel is a clutter simulation, and that is something we have to do using topographic data to model the reflections we get from the sides, because the radar sends a very broad beam, and you can get echoes off to the sides of the radar that track the spacecraft. So anyway, by going through the analysis and extracting basically a wave velocity through the material by knowing the topography that it's going through, the height of these cliffs or these deposits, she was able to determine that it's consistent with a high ice content, 50 to 85%, in a very large area. And so this has been talked about as a potential landing site, along with Arcadia Planitia for both MLE and for sending humans. So one of the things I will note here is that, or point out, is that the surface return is a little fuzzy. So even though the vertical resolution of Sherrod is theoretically 8.4 meters in ice, effectively, it's really hard to see anything very close in the shallow subsurface because you're kind of swamped by the fuzziness of that surface echo due to surface roughness, and the strong echo at the surface can mask something shallow. So hence we have what we call the blind zone. Various remote sensing data gives us information maybe down to about a meter. You know, things like spectroscopy, and then Sherrod, you can do something with the surface returns to probe a few meters down, like because the surface echo is really sensing not just the actual physical surface, but it's long wavelength, and so it's got a skin depth of several meters. And Cyril Kramer is an expert on this, and so he can tell you all about it. But that'll get you down a few meters to give you the bulk. You have to take into account surface roughness and things, but you can get an idea of what the bulk density is basically, or the dielectric constant, which can help you discern ice from other materials. But then you can't really see anything below or down to about 20 meters or discern any interfaces with Sherrod. So you get a gap here, and that's a really important interval for designing these missions, right? So we don't really have data in that interval. Geomorphology gives us indications of processes that involve ice going down to hundreds of meters. And I'll get into this later, but the mission that they are proposing to send to Mars, called International Mars Ice Mapper, has a high frequency radar that will probably only get down a few meters. This is optimistic, I think. So let's switch gears a little bit, because I like glaciers, and I think that they are perhaps a better target for these purposes than discontinuous sort of permafrost-like deposits in the plains. Glaciers on Mars are big anomalies. There's no way to grow glaciers in the present climate at the middle latitudes, so they're definitely you know, vestiges of past climates where ice was stable at the middle latitudes. It's way too cold to flow. Like maybe you could get microns per year right now. maybe millimeters if you're lucky, but you know, they just should not flow. And so when these were first seen in Viking imagery, the interpretation was that they were debris flows, lubricated perhaps with like maybe up to 10% ice that was deposited out, you know, basically diffused in from the atmosphere, settled into the ground, and then helped lubricate these debris flows, and then maybe that ice is gone. So they called them lobate debris aprons, which is unfortunate because we now know that they're basically glaciers, debris covered glaciers. Can't see any ice anywhere. If there's any ice exposed, it would sublimate away very quickly. So be careful when you're naming new features. Don't give it a genetic name, give it a descriptive name. There's all kinds of features. This is just an example from a recent paper that had some convenient figures, but lots of craters with concentric crater fill scattered throughout the region in the middle latitudes that should exhibit some viscous flow. Really kind of valley glaciers, these aprons that surround massifs, that's the one we were just looking at, and then lineated valley fill. So they're like basically valleys filled with this viscously flowing material. This is a map put together by Joe Levy, who many of you know, mapping these features in the middle latitudes and classifying them as lobate debris aprons, and then lineated valley fill and concentric crater fill. So there's thousands, and they're big. Speaking of big, here's one that I've studied a lot in the southern hemisphere called Rufus Mons. And the city, Austin city limits, the actual city limits, not the festival boundaries, are plopped in here to scale. So this is one glacier complex. The vertical exaggeration here is about 6 to 1, but you can get a sense for the size. So you could plop a colony down here and mine water ice basically forever if you wanted to. We're going to zoom in on that feature successively using some CTX imagery. And you can see these viscous flow features clearly. This stuff is flowed in the past. There's impact craters on the surface that are not deformed. They may have like relaxed some, but they're still circular. So you can see that they're not flowing recently. But anyway, I'll get to this later, but I just want to mention it now. We have beautiful morphology, and with high-rise stereo imagery, we can get detailed, like meter scale topography over, you know, areas about that size. We've got, as I'll get to, bulk composition from Sherrod. And so what I would love to be able to do is basically interpret this morphology as a flow history and maybe climate history. There's signals in here, like there's really good information in these ridges. But we're not there yet, working on it. So this is some of the first Sherrod data we acquired over one of these. On the top is the splatter simulation, so you can kind of ignore that, but it's basically confirmed that what we see in the radar data in the subsurface are real reflections from the subsurface. And so what you see is a really sharp upper surface. There is a little bit of clutter here that does actually correlate, but you've got a sharp, in general, a very sharp upper contact with the radar, distinct echo, and then nothing, and then a base. And this is in time delay. This is a converted to depth because all we have is time. But I don't have time to get into it, but we can show through various means that the properties are consistent with water ice, the wave velocities in particular, but then also the losses. So this was our first view into one of these, and it's like, boom, this is a glacier. It's not a debris flow. My student Eric Peterson did this survey of hundreds of them because one is definitely not enough. It's enough for a science paper, but not, you know. Anyway, I joke about that. Like, stop at one, write the science paper, don't collect any more data. But this was, it's kind of true, right? But this was the, okay, let's look at a bunch of them, do the statistics. So this is in the northern hemisphere along the dichotomy boundary, called Deuteronalis Mensae. Just vast numbers of these glaciers. This is the blue is what was mapped by Joe Levy based on morphology. This is the Sherrod coverage. All the yellow is where we had basal detections. The red, we don't. And he wrote another paper explaining that with surface roughness. If it's too rough of a surface, you don't get the energy through it. But he did basically the wave velocity calculations and the loss tangent, which is a measure of how much power you lose. And for freshwater ice that's at Mars temperatures, you lose like almost no power as you're going through it. So this is just a plot of the data for the dielectric constant, which is basically this one showing that it matches the 3.0, which is very close to pure water ice. So I think the number in the end was like 86% or higher water ice for all of these together. All right, age. This is from a very recent paper, and I was just chatting with Tim Gouge about it. Based on other studies, crater counting, which is very difficult to do on these because they tend to wipe out the craters. We thought that they are potentially up to 1 billion years old. This paper is saying that some of them are up to 3 billion years old. Tim is skeptical. So we'll see, but they do span a range of ages from a few million years old to hundreds of millions of years old, which I think makes them super interesting for paleoclimate. The ice in the northern plains that these craters are excavating, their impacts and landers and the icy scarps are probably much younger. We don't know, but probably a few million years maybe. We're not really sure, but it's probably most likely it's much younger than these older glaciers. So I think that makes them very interesting for paleoclimate. And in most cases, we don't see internal layering. That could be an issue with the radar resolution and sampling along track and integration, but we do in some places see evidence for older units. So in this case, we've got, and this is again, Earth's Mons, and this load right here, and I forgot to put it in here, but I had a master's student, Enrico Quartini, who actually did a bunch of work mapping this out. And we're resurrecting that work and building on it now. But it looks like there's an older unit underneath a younger glacial unit. So our thought is if this actually makes it out to the surface out here in the plains just beyond the edge of the glacier, you could sample that. And so my student Roberto actually just got a NASA fellowship to work on finding the oldest ice in the mid-latitudes. And he's working on compiling the Sherrod data into a 3D data volume, like has been done for the polar caps, and people do it in seismics all the time. So we can analyze these interfaces in 3 dimensions because we now have so much coverage of these features in places because we've been targeting them for 17 years that we can build these 3D data volumes to do that. So I think that would be a cool place to go sample. All right, so what do we know? Radar properties are consistent with recovered glaciers rather than ice lubricated debris flows. The debris layer on the top, because of that singular echo, is probably less than 10 to 20 meters thick. People have looked all over and not found like an echo from the bottom of a debris layer. So it's either relatively thin or it's a gradual change. And that's one of our reasons to look at terrestrial analogs. Because we don't know. Clearly remnants of past climate, and that might be interesting. And also this relatively thin protective layer can preserve ice for a very long time. That's not a surprise, I guess, anymore. So I don't know. I think these would be a much better target. And they are discussed sometimes, but people are worried about the debris thickness because it's massive ice. Hundreds of meters, up to a kilometer in places. If you're going to send people there, you can set up a well. I think this is what they use at South Pole. You pump a little bit of hot water down, you start melting a lot of ice, and you basically have this reservoir that you just draw from, and it persists for a long time. Because they're talking about doing things like sending excavating equipment, you know, to the plains areas and like scraping off the surface, basically like open pit mining the ice, processing it and separating it. You know, it just sounds super complicated. This seems way simpler. So there actually are people looking into this now for Mars. But you could set one of these up on one of these glaciers and have unlimited water. It's also older ice, which I don't know. I'm not an astrobiologist, but it seems like we're going to look for life, extant life on Mars in this part of Mars history, not the, you know, evidence for past life in the old part of Mars like we're doing now. Then why not go to the oldest ice that exists where it's had the longest time? And I don't know. Seems like that would be better. And to me, it's more interesting for paleoclimate. If you could sample that ice and study it. All right, so we still don't know much about the surface layer, how thick it is, what the variability is, what we can learn from paleoclimate. Like I said, inverting the surface morphology for flow history. We don't really know how they flowed. I mean, if they're really a billion years old, you could flow that slowly and build up these features, maybe. But seems like more likely it's been episodic during periods where somehow it got warmer. And there is some evidence, I didn't get it in here, of places with wet-based glaciation. There's eskers. There's even places where it looks like there were melt channels on the tops of these. I meant to put that in here, didn't get to it. But they're very isolated, but very convincing. And so I think in some cases where maybe you had higher heat flow, like just due to the tectonic setting, or volcanism, you might have had wet-based glaciation. So those would be really interesting to look at. Okay, shifting gears. 6 years ago or so, we got a project funded and it's now ended, but to study debris covered glaciers. They're often called rock glaciers on Earth. When we first discovered this on Mars, I was like, oh, well, I'll turn to the Earth literature and learn everything I need to know about debris covered glaciers. And turns out there wasn't much literature. It was basically the same situation. People called these rock glaciers because you don't see any ice, and they just assumed they were mostly rock. And this is just comparison. Sorry about the lack of scale bars, but this is about maybe 2 kilometers long, about ½ kilometer wide at the widest. That's in Alaska. This is a similar size one on Mars. This actually flows out into a valley that has the lineated valley fill. So that's probably older ice down in the valley with this younger one coming out on top. So that's one of our study sites. There's another one in Wyoming I'll show you examples of. In each site we have 2 different rock glaciers facing different directions. Our guiding questions have been, how much ice is preserved in rock glaciers? When did it accumulate? What are the processes influencing the flow and the evolution? What can we learn about climate history? And how could we infer that from surface morphology and structure? And the goal would be to understand the entire system, how it evolves, how the surface morphology evolves, and then be able to go back to Mars and apply that and invert for climate history there. It's been a long road, and we've learned a lot and developed new techniques, and I can't go into all of it, but I'm going to give you some highlights. We've used GPR, now drone-based GPR, or recently repeat photogrammetry is huge to get the kinematics. We've used transient electromagnetics. We've used passive and active seismic. We've kind of just thrown everything at it. I'm going to focus on the GPR and a little bit on the photogrammetry results because they're super cool. This is how you do traditional GPR. Put out a tape measure, transmit, receive antenna. You move them like 25 centimeters, take data, move them 25 centimeters, take data ad nauseum. Students are awesome at this. And then we've also gone when there's snow on top, so you can actually ski with a sled. That kind of worked. And then mostly recently the drone, which I'm going to focus on more because it's the most Mars relevant. So as an example, and I really didn't even think this was going to work when we first went out there. I was like, really, we're going to get signal for these boulders? Like, no way. But it worked amazingly well. And so here's a little cross section near the toe of Sourdough Rock Glacier. You can see the bottom of the debris quite well. Below the surface here, you got ice rich material. And then you've got the bottom of the glacier with maybe some little channels underneath. Works pretty well. This is a cross section of one in Wyoming that we've looked at a bunch. And a lot of previous work has been done there as well. And going kind of off on the side here, this was following an old road. This is what the profile looks like, and this is the interpretation. You've got debris, a few meters on the top. You've got clean ice, and this section is kind of where it crosses more across the flow. And then you've got some layers of dirty older ice, and then you get down to probably the bed down there somewhere if we're seeing bottom. But in multiple places, it looks like we've got basically a younger unit on top of an older unit. And this lower part is actually pretty stagnant, and we think that's an old rock glacier. And then there's like a newer one that's on top. So that's kind of equivalent to the Mars case that I was describing. We can use the wave speed to estimate ice fraction using the mixing model. And this is just an example of several places we've gone to, different parts of some of these glaciers. This is an old stagnant lobe over here off to the side of Galena Creek Rock Glacier in Wyoming, and it's got very low ice fractions. And they follow a nice curve. And this is the most active part of these two in Wyoming that we're looking at. You've got ice contents over 90%. The newest thing that we've been doing, which is a lot of fun, and I also didn't think would work at all, but I had to try it, is a drone-based GPR. It's a drone about this big, fully deployed. It's got an 80 megahertz radar on it. We've added a radar altimeter and obstacle avoidance radar to do autonomous navigation, because we're flying at about 1.5, really usually 2 to 3 meters over the surface. 1.5 is a little scary. So over the few years, various tests, crashing it a few times, we've got a system that works pretty well. And you program in a flight path, and it goes. There's a little video. Let's see if it works. It's going to lag and Zoom. That's the problem. I was afraid of this. So this is going, looks great on my laptop. So this is down at the toe of Sourdough. It's difficult to walk here. Tyler's keeping an eye on it, but he can't go any further, and it just keeps going down the slope, about a couple of meters over the surface. Just give you a little bit of a sense of what the surface is like here. The boulders are huge, quite variable. And, I don't know if they're like this on Mars, but I think underneath whatever the recent stuff is on top, it's very likely something like this. And so even just drilling through that would be a real challenge, but people have done it on Earth. All right. Probably won't play the next videos because it just lags too much. So this is some drone radar just right there where that was flying down off the end. And it's not quite as beautiful as the regular old-fashioned, but you can see what you need to see. You can see the bottom of the debris, see down to the base, which I was pretty amazed with. So yeah, we can map out debris thickness, depth of the bedrock. This is in Wyoming. I guess I'll try the video a little bit just so you can get an idea of the surface there. It's a bigger rock glacier. And you can see these undulations. Those are the compressional ridges from the flow of this like 2-layer system, basically.
Look at detective light.
Right. And so it's our weather station. Tyler's very worried about it hitting the weather station. And I'll let it pan out. Let it turn the corner here so it pans out to so you can see the view. It's kind of I'll skip ahead a little bit. So it's up in this high valley, about 10,000 feet elevation. Pretty cool place. Yeah, it's funny. The mean annual temperature of this one in Wyoming is the same as the one in Alaska, even though it's lower latitude, it's much higher altitude. So works out really well. All right, I need to cruise. So this is just comparison of drone based and regular old fashioned surface GPR. This was done in about a day with a lot of fiddling with the stuff to, as we're getting it to work right. And then this is probably like a week's worth of traversing with the other system. But we're able to see depths of bedrock up to about 60 meters or so. We're measuring thickness as well. This is pretty cool. This is a comparison. This is one where the ground base definitely does a better job. But you basically can see most of it with the drone, but there's internal layers. This is the cirque, the high part of the glacier. And you get this series of layers that Eric Peterson published on. And what we think is going on is basically you get like periodic debris flows coming down, covering recent snowfall, and then it gets buried and then advected down. And so we would expect something like this perhaps on Mars as well. But we're not seeing it so far, at least with the radar we've got. Skip that video. Let's go up the cirque and get to the cool results. So we've been doing annual repeat imagery with drones and sometimes airplanes to do photogrammetry. We get a really high resolution orthophoto and a TEM. And then with the orthophotos, you can do change tracking and get the velocity field, which is awesome. So this is one of the ones in Alaska showing basically just a few months going to basically 7 years. And you can start getting a sense of the flow as you get more and more data, more time interval. They're flowing, maybe up to 1.8 meters per year here. Generally 1 to 2 meters per year is typical for these things we're finding on Earth. Focusing on the top one here, if you just do an extrapolation of the age or the velocity to get an age of the glacier, you think, how could it be an average velocity over its whole lifetime? It seems to kind of work because at Galena Creek, there's a couple of radiocarbon dates that match our plot in red, which is our calculation of the age of the glacier. So it comes out to about 3,000 years. That's pretty cool. But I think the even cooler part is looking at then interpreting internal layers. This is a longitudinal profile of GPR just up in this upper part of the rock glacier here on a velocity map. And you can see all these layers, and I know this is like maybe getting way out there in interpretation, but you could potentially assign ages to those layers and then correlate that with climate. And one of the things we want to do is try to do this in a site where we've got tree ring data nearby and see if we can correlate with it. Can't do that on Mars. But this is really cool stuff, and I wanted to get to this. With the flow field, you can calculate stresses or this and strains, and you can make strain maps. And so this is XX and YY. So XX is inward cross flow, YY is long flow. And so you can then interpret the surface morphology and the radar data in the context of the strains. And so the red here is compression this way and across the glacier. The blue is extension. And so you see these little like linear features, and wait, I had it backwards. Yeah, the red is inward and the blue is outward expansion. Anyway, so the pluses are places where we could hear water underneath the debris flowing like between the debris and the ice, which is also not really expected in current Mars, but maybe in the past. And so there's melt, there's a little bit of drawdown, and then there's some like it's moving in on itself right there. So you can see that in the strain maps. And then I'm going to zoom in on this part so we can talk about that. In this part of the glacier, you can see that, and overlaying on this is this ribbon is debris thickness. And so you can actually see where there's compression and extension on the surface due to the flow. And then you can also see it in the radar data. It's a little tough to see in here, but basically where you have compression, you get the debris layer like folding, like you get these, basically the layers getting squeezed together, and then it's spread out more where it's not. And so the really cool thing is you can basically, if you have a strain map, you can predict the relative layer thickness changes of the debris layer. And I think this is a direction towards, this is getting towards what we want to do on Mars. We've got the surface morphology, we've got the slopes, we've got the bulk composition. Maybe we can get at estimating strain rates, and then predicting where debris would be thinner and thicker, and then maybe we can get data to test that. The other part of this that's really cool is you can discern climate-based ridges. So there's those internal layers I was showing in the GPR data coming down, like they intersect the surface, and they're basically like boulder bands, and they cause ridges on the surface. And so one of the things for Mars, bit of a holy grail, is to know which of the ridges are due to internal layering and hence climate, and which are just compressional folding just due to the flow. And this is kind of brand new. Tyler's just writing this up. Stephen Tyler Manning graduated, but by combining the surface morphology and DM and strain map, you can figure out where these ridges are compressional and where they're likely to be climatic. And the climatic ones end up disappearing where you have high emergence due to the speed up and the dynamics of the glacier flow. So they basically get erased where you would think they would get erased. Like basically the layers get jumbled up inside, and then you lose the ridges. That was kind of a lot to go through. I hope it made some sense. But we're basically there. Like we've got we can do the mapping, we can see internal structure, you can see there's links between the internal structure, climate, surface morphology. And now we've got all the boundary conditions we need, put it all together and make a model of the whole system for multiple rock glaciers. So I think we're kind of ready to go back to Mars and start doing this. Obviously, we don't have the kinematics there, but we've got all the other pieces. So I'm hoping we can put it together and make it work with flow models, which there are a lot of people have done flow models. All right, so we need to get going here. I do think, like, given our experience with our drone radar and then success of the Ingenuity helicopter, things can get miniaturized. We'd probably fly one of these on Mars. So once you've picked an area to go land, you could deploy one of these and do a survey of the area and find the right spot. But we also need better orbital, like global type data, and to even pick those spots, right? And this has been discussed for a number of years. IMM, I don't know, I'm sure Cyril knows about it, but it's a mission that kind of came out of nowhere from NASA, and basically the Canadians wanted to send a radar to Mars, and they've got an L-band radar. They have a lot of experience with L-band radar, and so they basically are contributing the radar. People at headquarters wanted to make a mission out of it, and so then they got Japanese to contribute a spacecraft bus, Italians to contribute comms, and basically NASA's just running the mission and doing the launch, and then let NASA back out. Like, so yeah, typical. So there's no funding for it at the moment, and I'm not sure it will ever happen. But at the time the decadal survey was being written, the new one, NASA was absolutely confident this was going to happen. So you can ask me about that over a beer if you want. So would it work? Some people say yes. Some people say probably not. This is the line zone I was talking about in a different way, just shown a little differently. And so there's some frequencies plopped on here. I'll do it on the laptop. The L band would probably be around 900 megahertz. Based on modeling and assumptions about the regolith, the scattering properties and everything, maybe it'll see down a few meters. Probably not more than that. So previous studies looking at similar objectives concluded that P band, if you're going to do a SAR, you want P band, which is around 400 megahertz, to get deeper, down to, maybe 10 meters. So there was a measurement definition team for IMM. It's like NASA was like, okay, I guess we got to actually get scientists involved and tell us what we need. And their highest recommendation was to augment the L-band radar with a VHF radar sounder, which would get you just down in 100 to 200 megahertz. So it would definitely get you down into the tens of meters range. But again, will this ever happen? So basically the mission's growing. Of course, they wanted to add cameras and everything. So it's turning into a giant mission. Who knows if it'll ever happen. One of the problems with current radar sounder technology is that it's big and bulky and uses a lot of power. And the antennas are long, simple antennas that radiate broadly. And so it's difficult to know where your echoes are coming from. I won't go into all of this. And some, radars like Reason does have an array, but those are big and complex and it require a big spacecraft. So what else is out there? I've been working with people at MIT on trying to use the technology that they've developed for other missions called the vector sensor antenna. And it's super compact. This is a 6U spacecraft. So it's like that big. And the antenna pops out with a 2U volume, which is about that big. And it deploys into these multiple elements. And the really cool thing about it is that it measures all three components of both the magnetic and the electric field. And if you remember your basic physics, do the cross product of those two, you get the direction of the propagation. So you can detect the direction of arrival of the signal. Even if you transmit a broad pulse, your echoes that come back, you know where they're coming from. And so they've been using this for a passive mission that's just listening, basically pointing out into space and listening. And Mike Hecht asked me, could we make a radar out of this? And so we've been working on that for about 5 years. And so we have a couple of concepts in review right now that I think are also applicable to Mars. This is one for the moon, 40 to 70 megahertz. And the whole thing would be an 8U spacecraft, so still quite small. And you could target buried ice in the polar regions. And the cool thing is you can fly very low to the moon, and you can use the VSA to say, look into the crater walls if you wanted to. And you could just basically filter out the stuff you don't want to see and record the stuff that you do. Or you can send back all the data since it's the moon and you're close and do the processing and look at data from all the different directions. It's a very complicated figure, so I'm not going to go into all of it. But it's and then we have a lower frequency version in the works that would basically be for deeper sounding. And both of these have been developed to TRL, but 4 to 5 to 6, depending on the components. But we've done transmit testing of both, and so those are in review for technology development. Basically, if you wanted to send something like this to Mars, I feel like it would be an alternative to IMM that would be a lot cheaper, easier to implement, and it would achieve most of the objectives because you could basically get 3 times the resolution of Sherrod with the 40 to 70 megahertz version, and sounding, deal with clutter, map the shallow subsurface very easily. You could send multiple ones, like they're much cheaper. So this is in a nutshell. There's a lot of ice on Mars. it's in many forms. I think they're all interesting. Some people thinks it might contain life, which I don't know, maybe that would be awesome if it did. Glaciers are really weird and they're huge and interesting. And if we're gonna spend billions on a mission, or missions, I feel like we should know where to go. Like you don't go drill a random ice core on Earth, right? You do all these surveys, you spend years and years and years doing surveys to map out the ice layers and basal topography and figure out the right place to drill. You don't just randomly send something, right? Or based on very limited information. And if we're sending people, let's send them to a glacier. Why not? There's so much ice, and there are some at low enough latitudes that I think you could satisfy the engineers. You know, like 35 degrees ish to 40 degrees latitude. That's all I've got. I think that's it. Thank you very much for listening. I hope it was useful.
We got just a couple of minutes, so probably only have a chance for
Sorry.
a question. That's all right. Anybody in the room first? Go ahead, Rose.
Oh, no, you go ahead.
I said you first.
Yeah.
Okay, well, so would you argue for MLE to go to one of these or not? Because the debris cover would just be too thick.
Well, I think they need to drill deeper no matter what. But I think we need to know more about the debris layer thickness before you decide where to go. And the content, form of ice in the places they're talking about going now. Like they could drill in, it would be so discontinuous that they could miss ice by a meter. Like it's that unknown. And so before you send it anywhere, and I'm not necessarily advocating they go to glaciers, but I like the idea of going to older ice, like find the oldest ice that you can easily access. Easily meaning maybe within a few meters, 5-10 meters. But the drill, yeah, at the moment, the drilling technology is not good enough to say they can go that deep with that size spacecraft. So.
All right, one last one, then we have to probably clear the room.
Follow up on that, so you said there is a thin protective layer on top of the mid-latitude glaciers on North.
Yeah.
How thick do we expect those layers?
Well, based on our current information, you know, we claim that they're around 10 meters or less due to the resolution of Sherrod. You could maybe say up to 20 meters, but they might be just a few meters. We don't know, but just due to the resolution of Sherrod. Well, I mean, using your surface reflectivity, I guess you could maybe try to get an idea if they're more than a few meters or not. Yeah, obviously. But there may be some ways to get a better handle on it. The postdoc stuff, Neurotsi is kind of working towards that right now. And we could talk about this too, like split chirp with Sherrod and things like that, or changing the windowing and things. Yeah. But I also feel like we could maybe use some of our knowledge from terrestrial analogs to predict where it might be thinner. Anyway.
All right, let's thank Jack one more time.
Thanks.